3D data we can visualize very easily, but more than 3D we cannot visualize. Now, this 11 dimensional data are to be mapped to either 2D or 3D for the purpose of visualization, so that we can visualize what is happening on the surface of the objective function and the way the solution, the candidate solutions are moving on the surface of the objective functions towards the optimal value. Now, so that is the first objective for developing the visualized interactive GA. The next is to accelerate the GA search. Now, GA is computationally expansive, and that is why the GA is very slow. So, our aim is to accelerate the GA search to make it faster, and that is why we should go for the visualized interactive GA. Now, to develop this VIGA, so higher dimensional data are to be mapped into lower dimension. As I told that for the purpose of visualization, so you will have to map the higher dimensional data to the 2D or 3D, and once you have mapped the data to 2D or 3D, now you can visualize. You can approximately see the surface of the objective function, and now you can decide in which direction you should move by how much. Okay. Now, if you see the mapping methods, a huge literature is available on these mapping methods, and these mapping methods, it could be either the linear methods or the non-linear methods. So, in linear method actually 1:1 mapping is possible, but in non-linear methods we cannot get 1:1 mapping, and we will be getting some sort of approximate mapping. Now, regarding these linear methods, different methods are available or different approaches are available. Now, the out of all such approaches, the most popular one is the principal component analysis. In short, this is known as PCA. PCA is very popular. Now, there are some other methods like least square mapping, then projection pursuit mapping, and others. On the other hand, we have got a large number of nonlinear methods. For example, say Sammon's nonlinear mapping is also very popular nonlinear method, mapping method. Then comes the Visor algorithm, that is a graph based technique or the graphical technique. Okay, so you will have to solve graphically, and I will be discussing in details like how to map the higher dimensional data to the lower dimension using the Sammon's nonlinear mapping and the Visor algorithm. Now, another very efficient algorithm I should say for this nonlinear mapping is the self organizing map. In short, that is known as SOM, SOM, and this is a neural network, and that is very efficient mapping method from higher dimension to the lower dimension. Now, let me start with some of the nonlinear mapping methods, the working principle of some of the nonlinear method. Now, before I go for this nonlinear method, let me tell you the purpose, because here we will have to map from higher dimension to the lower dimension, like say from 20 dimension to 3 dimension or 30 dimension to 3 dimension. Now, if you want to do this mapping from a higher dimension to 2D or 3D, so this mapping is generally nonlinear mapping, approximate mapping, because exactly you cannot do the mapping from such a higher dimension to the lower dimension, and that is why for developing this VIGA, visualized interactive genetic algorithm, we took the help of actually the nonlinear mapping methods. Now, let me start with the Sammon's nonlinear mapping, and let us try to understand the working principle of this particular the nonlinear mapping method. Now, this Sammon's nonlinear mapping is a distance preserving technique. Now, let us see what does it mean. Supposing that I have got 2 points, the tip of my finger is point I, the tip of this particular finger is point J, and we try to find out the Euclidean distance between I and J. Okay. Now, supposing that we have got the Euclidean distance. Now, if you get this particular Euclidean distance, so this is one topology of the second point with respect to the first point. There could be some other topologies keeping the same Euclidean distance. For example, point 1 is fixed. Now, point 2 if I move, So, once again the Euclidean distance is the same, but topology is different. Topology of the second point is different from the first point. Similarly, the point could be here, the second point could be here, the second point could be here, keeping the same Euclidean distance, but the relative position of the second point with respect to the first point is different. Okay, that is called the topological information. Okay. Now, this Sammon's nonlinear mapping is actually the distance preserving technique. That means, we try to keep the Euclidean distance same, and we do not bother about the topological information or the relative position of the second point with respect to the first point, and this is once again an approximate method. Now, this error in mapping is minimized using a gradient descent method. You must have heard about the steepest descent method or the gradient descent method. Now, the optimization algorithm which I am going to use here is nothing but the steepest descent algorithm or the gradient descent algorithm. That means, we try to find out the error, and this particular error is minimized through a large number of iterations. So, this is an iterative method. It will take long time to reach that particular the optimal solution, but there is a possibility that you will be getting very accurate solution. So, error you can make it very small through a large number of iteration. So, that possibility is there. Now, here I am just going to discuss the problem scenario. Now, here I am just going to consider n data points, and each data point is in L dimension. Now, how to represent the n data points in L dimension? Now, this n data point is denoted by x I, where I varies from 1 to up to n. Okay. Now, here, so this particular I, that is the say I equals to 1, that means the first point, the first data point I am just going to consider. Now, this particular first data point is having L numerical values. Now, if I just write it here, it is something like this. Supposing that I am just going to write a particular solution, say x 1. Now, this particular solution x 1, if I want to represent the data point x 1, so I will have to take the help of L, capital L number of numerical values, like your x 1 1, x 1 2 and so on, then your x 1 L. So, there are L number of numerical values to represent a particular point in L dimensional space. And similarly, so I have got, so I equals to 1 2 up to n. So, capital N number of data points, and each data point is having L dimension. Now, what is our problem? Our problem is to do the mapping from this L dimensional space to this particular 2D or 3D. That means, on the 2D and 3D, once again there will be n number of capital N number of data points, but it will be in either 2 dimension or in 3 dimensions. Okay. Now, let us see how to do this particular the mapping. Now, you can see that the representation of the higher dimensional space, that is the L dimensional space. So, this is the way actually we represent the higher dimensional space. Okay. It has got many dimensions, and here you can see it is in 2 dimension, like y is a function of x only. So, if y is a function of x only, that is in 2 dimension. If y is a function of x 1 and x 2, that is in 3 dimension. Okay. So, here y is a function of x only. So, this is in 2 dimension. So, our aim is to do the mapping from higher dimensional space to the 2D. Now, let us see how to do this particular the mapping. Now, as I told that n data points in LD space can be represented as x 1 is, as I told, x 1 1, x 1 2, x 1 L. Similarly, x 2 is x 2 1, x 2 2, x 2 L. Similarly, x n is x n 1, x n 2, n x L. Here there is a mistake here. This should be x subscript capital N capital L. Now, similarly, the n data points in 2D plane are represented as follows. So, capital Y 1 is nothing but y11, y12, then comes y2 is y21, y22, then yn is actually yn1, yn2. Okay. Now, let us see the steps of this particular the algorithm. Now, our aim is to do the mapping from higher dimension to the lower dimension, say from L dimension to the 2 dimension. So, L dimensional information is there with you, but in 2D the information is not there, okay, and you will have to do this particular the mapping. Now, the first step is generate n data points in 2D plane at random. So, use one random number generator to generate capital N number of data points in 2D, and as I know in 2D to represent a particular point I need 2 numerical values. Are you getting my point? So, I will be generating 2 numerical values for one, okay, and similarly there are n such points. So, 2 multiplied by n, 2n number of numerical values using the random number generator. Okay. Now, step 2, calculate Dij star, that is the Euclidean distance between 2 points in LD, say xi and xj. Supposing that in LD, L dimension I have got 2 points I and j, okay. So, I can find out the Euclidean distance in higher dimension, and that particular Euclidean distance is nothing but Dij star, and that particular numerical value is known to us. Okay. Now, similarly, we calculate Dij, that is the Euclidean distance between the corresponding to mapped points in 2D, say yi and yj. So, xi and xj I am doing mapping to 2D. So, this xi will be mapped as yi, this xj will be mapped as yj. So, yi and yj I am trying to find out the Euclidean distance in lower dimension, and that is nothing but the Dij. Now, for perfect mapping, so this particular Dij star will be equal to the Dij, okay, the same Euclidean distance if it is error free mapping, but truly speaking we will not be getting the error free mapping, there will be some error, and this particular error is the deviation between Dij star and Dij, and we will represent this particular error in a particular fashion. I am coming to that, and this particular error in mapping has to be minimized through a large number of iteration using one gradient descent method or a steepest descent method. And if you can minimize this particular error in mapping, your purpose is solved. So, your n data points of the higher dimensional space you will be getting in 2D or 3D, okay, and there will be approximate representation of this particular higher dimensional data to the lower dimension. Okay. Now, step 3, as I told that there will be some mapping error and you cannot get the error free mapping. Now, this mapping error in mth iteration, that is denoted by em, is represented as 1 divided by c, capital C, summation I equals to 1 to n, summation j equals to 1 to n, I less than j, then this particular expression Dij star minus Dij m square divided by Dij star. Now, let me explain why do you use this type of expression. Now, this Dij star is actually the Euclidean distance in higher dimension which is known between the 2 data points I and j, and Dij m, that is the Euclidean distance between the 2 mapped point in 2D plane at mth iteration, okay. And the difference between Dij star and Dij m, it could be either positive or negative, and that is why we take the square of that just to make it positive, divided by this Dij star, as if I am just going to find out the rate of change. So, that type of thing, and this Dij star is known. So, this is the way actually Sammon represented this error at mth iteration, and this particular C is actually where C is summation I equals to 1 to n, summation j equals to 1 to n, I less than j, dij star. So, what is this particular C? Now, let me take one example. Now, supposing that I have got say 5 data points. So, if I have got 5 data points, so how many such distance values are possible? If there are 5 points, so the distance values which are possible are as follows. For example, say there could be the distance between 1 1, that is 0, Euclidean distance is 0. There could be distance between 1 2, 1 3, 1 4, 1 5. Then comes here 2 1, 2 2, 2 3, 2 4, 2 5. Then comes 3 1, 3 2, 3 3, 3 4, 3 5. Then comes 4 1, 4 2, 4 3, 4 4, 4 5. Then comes 5 1, 5 2, 5 3, 5 4, 5 5. Okay. So, if there are 5 points, there are 25 such distance values possible, and out of these 25 values, if you just represent with the help of a matrix, the diagonal elements, for example, say this 1 1, 1 2, 1 3, 1 4, 1 5, these are the diagonal principal diagonal elements. Here the distance values are nothing but 0. Now, if we concentrate on the left hand side of the principal diagonal or the right hand side of the principal diagonal, how many distance values are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, there are 5 square, there are 5 points. So, there are 5 square Euclidean distance values. Out of 5 square, that is 25. There are 5 diagonal elements where the distance is 0, others could be non-zero. Okay. Now, out of these 5 square, that is 25, if I concentrate only on one side of the principal diagonal, so there are 5 C2 distance values, that is your 5 factorial divided by 3 factorial, then comes 2 factorial, and this is nothing but 5 into 4 20 divided by 2. So, there will be 10. So, these 10 distance values I am going to consider. So, this particular C is going to represent that one side of the principal diagonal matrix. Okay. The principal diagonal, that is why C is equals to summation I equals to 1 to n, summation j equals to 1 to n, I less than j, dij star. Okay. Now, this dijm is nothing but is your square root of summation k equals to 1 to d yikm minus yjkm square. So, this is actually the Euclidean distance in 2 dimension or 3 dimension corresponding to the mth iteration, and this particular error. So, we are going to minimize iteratively using the steepest descent method or the gradient descent method. I think this is clear to all of you. Now, step 4, the mapping error is minimized using a steepest descent method, and what is the rule for updating? Y p q m plus 1 is equals to y p q minus m f delta p q m. Now, this m plus 1 is m plus 1th iteration, m plus 1th iteration. Okay. Now, this y p q m plus 1 is nothing but y p q m minus m f is nothing but the magic factor, and the value of the magic factor will vary between 0 and 1, and that is nothing but the step length. If you remember the steepest descent method, there is one step length and search direction. So, step length is denoted by this particular the magic factor m f, and this delta p q m, that is nothing but the search direction. Okay. And here we are moving opposite to the gradient direction, and this is a minimization problem. Our aim is to minimize the error in mapping. Okay. So, this particular EM, that this is the error in mapping, we are trying to minimize through a large number of iterations. Now, this delta PQM is nothing but you can see that the partial derivative I am using divided by the mod value of the second derivative. Okay. So, this is nothing but your this shows the gradient information, the gradient direction, and here I am using one negative sign opposite to the gradient direction, and we want to minimize. So, this particular error in mapping. So, this is actually the rule for updating. Now, this particular method is an iterative method and computationally very expensive. Our experience says it generally take 100, 150 iteration to give you a very accurate mapping. Okay. But you will be getting very accurate mapping using this particular the method. And now, I am just going to discuss another method of mapping, that is also a nonlinear mapping, but here the error in mapping may not be so much good, but this particular mapping is done only in one iteration and it is very fast within a fraction of second. So, you will be getting this particular mapping from higher dimension to the lower dimension, but you may not get a very accurate mapping. Okay. Now, the second method, that is the Visor algorithm. Now, as I told, this is a geometrical method, the graph based technique, graphical method. Okay. And here in this particular method, we are going to use once again the distance information, and this is once again a distance preserving tool, and we do not consider the topology. Now, let us see the working principle of this particular method. The working principle of this particular method, to explain, now once again I am just going to take n dimensional data, sorry, L dimensional data, and there are capital N number of data points, and those are represented as follows. And our aim is to map, so this particular data to 2D for the purpose of visualization, so that you can visualize. You see, if you remember the original problem, your objective function which you are going to maximize or minimize using a genetic algorithm, that is in higher dimension. So, that higher dimensional data space or the objective function space I am going to visualize on the 2 dimension or the 3 dimension. Okay, so, that is actually my M. That is why I am taking the help of all such mapping methods. Okay. Now, here, so this particular method I am just going to draw it here, that will be easier for you to understand. Now, supposing that I have got capital N number of data in L dimensional space, and let me represent this particular data points. So, this is in L dimensional space, this is in L dimensional space, and I have got a large number of data points. I have got a large number of data points, capital N number of data points. It could be 1000, it could be 5000, it could be 10,000, something like that. So, we have got a large number of data points, and all of you know how to represent this type of data points. To represent one data point, we need L numerical values, capital L numerical values. Okay. Now, this particular data points we will have to do the mapping to the 2D plane. So, x and y say. So, that is actually our M. Okay. Now, let us see the steps to be followed to do this particular mapping using some graphical method. Step 1, locate the pivot points V1, V2 and V3 in LD space, which is a convex enclosure to the remaining data points. So, how to represent this V1 or how to get this particular V1, V2 and V3, which are nothing but the pivot points. To get the pivot points, we take the help of these steps. Compute centroid M of all data points N in the original LD space. What does it mean? So, I have got capital N number of data points, and now I will have to find out the centroid of capital N number of data points. So, how to find out this particular the centroid M? Now, to find out the centroid M, actually what you will have to do is, so you will have to concentrate here. So, here you see this is the first dimension of the first data point x11, this is the first dimension of the second data point x21, this is the first dimension of the nth data point, that is xn1. So, what we do? We try to find out the average or the mean of the first dimensional data, that is we try to find out the average of x11, x21, xn1, we add them up and divide by the capital N, because we have got capital N number of data points, okay, and that will be the average value corresponding to the first dimension. The same procedure you follow for the second dimension, third dimension, up to the nth dimension, okay, and then you will be getting the coordinate of the centroid, that is M, and supposing that, so this is the data points, might be the centroid could be here. So, centroid is denoted by capital M, okay. So, compute centroid M of all the data points n in the original LD space, determine the pivot point V1 such that the distance between V1 and M is the maximum of all distance values between Vi, small vi and M, where I varies from 1 to n. What does it mean? Now, M is known. So, from M we try to find out the Euclidean distance of all capital N data points. So, how many Euclidean distance values will be getting? Capital N number of Euclidean distance values, and you find out the point for which you get the maximum Euclidean distance values, and that particular point could be the first pivot point, and that could be your V1, supposing that V1 is here. Okay. So, V1 is a point which is having the maximum Euclidean distance values from the centroid M. I think this is clear to all of you. The next is determine the second pivot point V2 such that the distance between V2 and V1 is the maximum of all the distance values between Vi and V1, where I varies from 1 to n minus 1, because one point I have already taken as V1 out of capital N point. So, I have got remaining n minus 1. So, from this particular V1, so I try to find out the Euclidean distance of all n minus 1 data points, and once again we try to find out the point for which we get the maximum Euclidean distance starting from V1, and supposing that that particular point is say V2. So, V2 is nothing but the second pivot point. Now, next we try to find out the pivot point V3 such that the distance between V3 and V2 is the maximum of the all distance values between Vi and V2, and thus V3 is such a point that this should be at a maximum distance from V1 also. So, we try to find out a point that is V3 which is at a maximum distance from V2 as well as it is as maximum distance from V1. Okay. So, approximately actually we try to find out these particular pivot points, that is V1, V2 and V3. Okay. Now, next is step 2. Locate the pivot points P1, P2, P3 in 2D plane corresponding to the points V1, V2 and V3 respectively. Now, this is in L dimension space and this is in 2D. Now, in LD we have got the pivot points. Now, you will have to find out the pivot points in 2D plane. So, how to find out the pivot points in 2D plane? To find out the pivot points in 2D plane, what we do is we try to find out the Euclidean distance between the origin in higher dimensional space, origin at V1, the distance between origin and V1, then we find out the Euclidean distance between origin and V2 and origin and V3. So, I will be getting 3 Euclidean distance values, and keeping that particular Euclidean distance values, we try to draw 3 circular arcs in 2D plane. So, might be the first circular arc could be here. So, this could be the first circular arc corresponding to the Euclidean distance between the origin and V1. Now, this could be the second circular arc, that is the distance between the origin and V2, and this could be the third arc corresponding to the distance between origin and the point V3. Okay. So, we will have to draw 3 circular arcs. Now, we concentrate on the first circular arc. Now, on this particular arc, we have got a large number of points. Any one you can select as a starting point. So, let me consider that this is the starting point. So, this I am just denoting as point P1, the first pivot point corresponding to this particular the V1. Okay. Now, I know the Euclidean distance between V1 and V2. So, considering this as center, that P1 as center, so I can draw one circular arc considering this as the radius, that is the distance between V1 and V2. So, I will be getting one circular arc here, and this particular point is nothing but your P2, the pivot point P2 corresponding to V2. Similarly, I can find out the distance between V2 and V3. So, I can find out the distance between V2 and V3. So, considering this as center and the radius is the distance between V2 and V3. So, I can draw one arc, and here I will be getting the point P3. Okay. So, approximately I can find out the pivot points in 2D plane, that is P1, P2 and P3 corresponding to V1, V2 and V3 respectively. Now, you see I have got capital N number of data points. Out of this capital N number of data points, 3 points I have already mapped corresponding to V1, V2 and V3. I have already got P1, P2 and P3, and now I will have to do the mapping for the remaining n minus 3 points. So, how to do the mapping for the remaining n minus 3 points? Now, step 3, mapping of the remaining n minus 3 points will be done as follows. Say the point V of LD space is to be mapped to a corresponding point in 2D plane. Draw the lines V1, V2 and V2, V3. Draw 2 perpendicular lines from the point V to the straight line V1, V2 and V2, V3. Thus, the point K1 and K2 are obtained on the lines V1, V2 and V2, V3 respectively. So, I am just going to follow this particular. So, please listen it to me very carefully. Supposing that I have got a particular point, say point V, say any point I will be taking out of n minus 3, say any point I am taking as point V, and this point V I will have to map in 2D plane. So, how to do? We join V1, V2 by a straight line. Similarly, we join V2 and V3 by a straight line, another straight line, and from V you draw the perpendicular on V1, V2, and so I will be getting a point that is your K1. Similarly, from this particular point V, so I will be getting another perpendicular, and I will be getting this particular point as K2. So, I am getting the point K1 and K2, and once I have got this particular point K1 and K2, so very easily I can find out what is V1 K1 ratio K1 V2, and I can also find out what is V2 K2 ratio this particular K2 V3. And next what we do is we join the line P1 and P2 by a straight line, join these points P2 and P3 by another straight line. Okay. And now I am just going to locate a point on P1, P2. Say this particular point is your say D1. So, this point is D1. Now, this point D1 is such a point, so that this P1 D1 ratio D1 P2 is same as the V1 K1 ratio K1 V2. Similarly, I am just going to locate another point say D2, and this point D2 is such, so that this P2 D2 ratio, this D2 P3 is same as the ratio of V2 K2 ratio K2 V3. So, I am able to locate the points D1 and D2 on the lines P1 P2 and P2 P3 respectively. And once I have located the points like D1 and D2, so what we do is we try to draw some perpendicular. So, we draw the perpendicular to the line P1 and P2, at the point D1. So, this is at 90 degree, and similarly you draw another perpendicular at the point D2 on the line P2 P3, and these two perpendiculars are going to meet at a particular point, and that particular point is your point P. So, by doing this, the point B in a higher dimensional space, we can map it approximately to the point P in 2D plane. Okay. And this method has to be repeated for the remaining n minus 4 points, because 4 points I have already mapped, like your P1, P2, P3 and P also I have mapped. So, I have got remaining n minus 4 points. So, this method, the method of whatever I told, so you will have to repeat for n minus 4 times, okay, so that approximately you will be able to do the mapping from higher dimensional space to the lower dimensional space approximately. As I told several times, that accurate mapping is not possible, okay, because from higher dimensional space, if you want to do the mapping to lower dimension, so 2D or 3D, so we will have to be happy with the approximate mapping. Very accurate mapping or exact mapping we may not get. Okay. So, I think this particular mapping method is clear to all of you. Okay. Is there any doubt here, please? Please, one after another. Yes, yes. Yes. Now, actually as I told, no, so this has to be done graphically, but how to implement in computer program? This is a very good question, like how to implement in the computer program. So, actually what I do is, you will have to use the principle of coordinate geometry. See, if I have got a 2 points, one coordinate is x1 y1, another is x2 y2. Okay. So, I can find out the Euclidean distance using coordinate geometry. I can find out the expression, the mathematical expression of the straight line joining the 2 points x1 y1 and x2 y2, and mathematically I can find out what is the equation of the perpendicular also. This is very simple coordinate geometry in 2D. Similarly, in LD also, so you will have to follow the principle of that type of coordinate geometry, okay, and you will have to find out the equation of the straight line, the perpendicular to that, okay, find out the intersection. So, all such things you will have to do analytically, and whatever final expressions you get, that you will have to write down in the computer program, because computer program does not know anything. So, you will have to solve everything analytically, and whatever final expression you get, that has to be written in the computer program. See, it has to be solved using the computer program. It is a graphical method, but computer program does not understand the graphics. Okay. So, that has to be converted to the analytical approach. Okay. So, analytically you will have to solve, find out the equation of the perpendicular, find out the intersection point and all such things, and that has to be written in the computer, the program. Okay. Is it clear to you? Yes, it is possible, mathematically you can find it. 3 dimension very easily can find out, you know, up to 3 dimension, you have studied up to 3 dimension. Following the similar procedure, you can also do it for higher dimension. It is possible. In 3 dimension it is possible, you have studied up to 3 dimension. Why did you study up to 3 dimension? Because we can visualize only up to 3 dimension. 4 dimension and above we cannot visualize. That is why we generally do not study also. Okay. Up to 3 dimension, how to find out the equation of a straight line passing through the 2 points having the coordinate x1 y1 z1 x2 y2 z2, you can find out. Okay, you can find out the perpendicular. Same thing you can do it for in higher dimension also. Please.
So, once we have mapped our n dimensional points to 2 dimensional, 3 dimensional, then we analyze those points and the local minimum.
Yes, yes, I am coming to that.
Then, I mean, how can we remap those points to?
I am coming to that. We will have to use a reverse mapping. I will be discussing that in details. Okay. So, you will have to do from higher dimension to lower dimension, but GA is working in higher dimension. So, once again from lower dimension you will have to go back to the higher dimension, that is called the reverse mapping. How to do reverse mapping I will be discussing in details. Okay. Just a minute.
So, if we take a point V4, would that be able to, would we be able to say that we could map a three-dimensional instead of, like we use V1, V2, V3?
Yes.
To map a 2D space.
Now, V1, V2, V3 those are in higher dimension, L dimension, and we are mapping to 2 dimension P1, P2 and P3. Here for simplicity I have considered 2 dimension, you can also consider 3 dimension. We generally go up to 3 dimension.
And how could we be sure that, so this one makes it sure that V1, V2 is perpendicular to V2, V3, the thing we did on the right.
Actually these are all approximate mapping, these are all approximate mapping. Okay. Accurate mapping you cannot do from such a big space, higher dimensional space to 2D or 3D, you cannot go for 1:1 mapping, it has to be approximate. Okay.
The last part, how you plot the other points in the 2D plane, can you explain that one?
Other points in 2D plane. The way we just did the mapping for the point V, the same method we are going to repeat for n minus 4 point. Actually what you do, whenever you write down the computer program, we just put it in for loop. For I equals to this, that type for loop. Inside the for loop we put, for the remaining n minus 4 points we follow the same method. Okay. So, this is in for loop, in the computer program this is in for loop. Okay. Please. Point P3, yes. Yes, yes, you are right. Now, to get this particular point P3, we took the dimension like V2, V3. We can also take the distance between V1, V3 also. And if I take the distance between V1 and V3, there is every possibility I will not be getting the same P3. I will be getting a different point as P3. That is why this is an approximate mapping. This is an approximate mapping. I consider the distance between V2 and V3 just to locate P3, but I did not consider the distance between V1 and V3, that is another possibility. And if I take the distance between V1 and V3, I will be getting altogether a different point as P3. Okay. So, the point P3 will be slightly different, and that is why this is an approximate way of doing. And several times I am mentioning accurate mapping is not possible from higher dimension to the lower dimension. Okay. You can take any one.
So, this P3 that we get from V1, V3, will that be like very different from the normal P3 that we got, or
slightly different, slightly different. See, as I told, these are all approximate mapping, but this approximate mapping is going to help us to develop that particular figure. I am coming to that. Okay. The purpose of discussing this particular mapping methods is how to develop that particular the visualized interactive genetic algorithm, which will be very fast compared to the ordinary genetic algorithm. So, this is the higher version of genetic algorithm. The genetic algorithm which you have already studied, this is a modified version or slightly higher version of that. Now, here actually the mapping is done in one iteration, and it is faster than the nonlinear Sammon's nonlinear mapping. Now, here I am just going to take one example. So, this is Schaeffer's F1, Schaeffer's test function, y is 0.5 plus sine square root summation I equals to 1 to 4 xi square minus 0.5 divided by this. So, here you can see I varies from 1 to 4. So, this is in 5 dimension. So, this particular function is in 5 dimension. This is the plot of this particular function, but this plot is once again 3D plot. 5D plot I cannot take. So, this is the 3D plot, and this is a very complicated function. Okay. Now, using this Sammon's nonlinear mapping, if you do the mapping to 2 dimension, I took 1000 points. So, 1000 points are mapped to 2D using Sammon's nonlinear mapping, and these 1000 points are lying on the surface of the Shepard's F1, the test function. Okay. And this is how to get the mapping using Visor algorithm, which is a graph based technique. Now, here you see the points are very distributed. So, it is very easy to visualize, but here you can see the points are clubbing together. So, it is not so easy for the purpose of visualization. Are you getting my point? So, Sammon's nonlinear mapping actually gives better visualization, but at the cost of computation. Are you getting my point? At the cost of computation, and here you will be getting slightly less accurate, I should say, but here the method is very fast. Okay. Now, using these mapping tools, so how to develop this particular the visualized interactive GA. Now, you can see that here GA is acting or working in the higher dimensional space, and I have got an objective function that y is a function of 10 variables x1, x2 up to x10. So, GA is working on the higher dimensional space. Okay. Now, this higher dimensional data that is mapped to 2D using the mapping methods, say Sammon's nonlinear mapping or Visor algorithm, and here on 2D. So, I will be getting this type of information of the topology or information of the objective function. Now, this particular thing was actually implemented on OpenGL. So, on the computer screen, one rectangular box will come, and there you can see that all such data points, and if you just click here with the help of the mouse, you will be getting the fitness information, the value of the objective function. For example, if I just click it here, so I will be getting the value of the objective function. If you click at another points, you will be getting the value of the objective function. Sorry. So, this particular user is going to see this particular information, like in which direction the value of the objective function or the value of the fitness is going to increase, and supposing that this is a maximization problem. Now, if you can visualize that in this particular direction the value of the objective function or the value of the fitness is increasing, we need not go to the other side of this particular search space, and we give the information to the GA that you concentrate your search only in this region and do not go to other region, might be the maximum solution or the optimum solution is lying here only. So, this particular local information we give it to the GA, but how to give this particular information to the GA? The GA is working in higher dimensional space. To give this information, so we will have to go for reverse mapping as mentioned by you. So, these 2 dimensional data are to be mapped to the higher dimension. So, how to do? I am just going to explain that. So, once you have got this particular reverse mapping, so this 2D data I will be getting in LD, and we are going to give some information to the GA that you concentrate your search only in this region, and please do not go to the other side of the region. And by doing that, actually I am just going to inject some information to the GA, and by doing that actually the search speed of the GA is going to be increased. And we implemented actually on a number of test functions, okay, and we have seen that this particular Vega is found to be almost 5 times faster than the ordinary binary coded GA or simple genetic algorithm. And we have tested on a number of actually test function. Of course, the performance of this particular Vega is found to be function dependent, okay, but it could give that particular optimal solution bit faster. Okay. Now, later on we also developed this Vega was developed by us only, myself and Professor Takagi from Japan, Kyushu University, he is a professor there, and later on we implemented on a number of test functions, okay, and we also implemented some other mapping methods also, which I am not going to discuss. We also actually developed another mapping method, which I am not going to discuss here. Now, let me tell you like how to do this particular reverse mapping. Now, to reverse mapping we will have to use some sort of lookup table. Okay. Now, how to implement the lookup table? Let me explain that. Now, what is there in forward mapping? Supposing that, so I am just going to write it here. In forward mapping, supposing that I have got some information in the first dimension, second dimension, third dimension, fourth dimension. Similarly, this is the nth dimensional information, the numerical value, and I have got its corresponding 2D numerical value. For example, one could be this information, another could be this information. So, from LD to 2D, I have got this particular mapping, forward mapping. Similarly, another point. So, I have got some mapping here, LD to 2D. Similarly, we have got a large number of points. So, the last point let me consider. So, the information is as follows. So, this is the forward mapping. Now, how to carry out the reverse mapping? To carry out the reverse mapping, actually what we do, supposing that LD to 2D information we have got, and that particular user is going to give one information that you concentrate your search here, and there is a possibility you will be able to get the optimal solution very soon. And supposing that that particular 2D information is here, let me assume. So, if it is here, so I will have to find out approximately its corresponding LD information. How to find out? We take the help of interpolation. So, through this interpolation, approximately we can find out what should be this particular the higher dimensional value approximately. I use this information, do the interpolation, and we try to find out what should be the approximate the higher dimensional values, and those higher dimensional values we are supplying it to the GA. Okay. So, this is the way actually we are trying to implement. So, we implemented this particular the figure. Now, one new direction I am just going to tell you. Now, what we are planning to do is we are going to replace. So, this particular human operator, the user, by one fuzzy reasoning tool, and we are going to make this particular GA intelligent. Okay. So, we are going to replace this particular human user by one fuzzy reasoning tool, and we are going to develop one tool that is intelligent optimization tool or intelligent genetic algorithm or intelligent particle swarm optimization. Okay. In fact, we have started working on it, not much progress has been made in this particular direction, but we are going to do it. Okay. One PhD student is going to join soon in this semester. So, most probably he is going to tackle that particular the problem, like how to design and develop one intelligent genetic algorithm or one intelligent particle swarm optimization. So, that depending on the nature of the objective function, it can tune its parameter and perform accordingly. Generally, the performance of the GA or PSO is found to be function dependent. Okay. So, it depends on the function, the objective function, and intelligent optimization tool will be independent of that particular function. So, you supply different types of functions, accordingly it will adjust these parameters, okay, and will try to perform in the optimal sense, and it will perform more or less equally well for the different objective functions. Okay. And that will be intelligent genetic algorithm or intelligent particle swarm optimization, which will be implementing in future. Okay. Like the extended version of this particular the study. Okay. Now, let us do one thing, let us go for T. After T, we are going to start with your the serial GA. Okay. হ্যালো হ্যালো মাইক্রোফোনটা আসছে না এটা কি ফার্স্ট স্টেপে এসেছিল সাউন্ড সাউন্ড ঠিক আসছে হ্যাঁ hello now we are going to start with another GA I should say this is called the scheduling GA because the problem of scheduling is much more difficult compared to the ordinary optimization problem and the GA which is to be used to solve the scheduling problem is slightly different. Its operator crossover operators are slightly different, okay, and that is why I just called it this is a scheduling GA. Now you have already studied about the different crossover operators like single point crossover, 2-point crossover, multi-point crossover, uniform crossover, okay. Now here for the scheduling problem, so this type of crossover are not going to serve the purpose and we will have to use some special type of crossover operator. Now what is the reason? The reason I am just going to tell you now. Now let me define that scheduling problem. Now this scheduling problem is a special class of optimization problem in which not only the position of different elements, but also their order and adjacency are important. Once again let me read it out. A special class of optimization problem in which not only the position of different elements, but also their order and adjacency are important. Example is TSP, traveling salesperson problem. Now this is actually an optimization problem. The problem is such, supposing that there are 10 cities. Now one salesperson will have to touch all 10 cities by covering the minimum distance, okay. So that salesperson is going to touch all 10 cities once by covering the minimum distance. So how to find out the optimal sequence, okay. So that type of problem. Now here if I consider 10 cities, so cities are having relative position also. For example, if I consider Kolkata and Delhi, Delhi is towards north with respect to Calcutta. So not only the Euclidean distance between Calcutta and Delhi, okay, but its relative position is also important. The Delhi is towards north with respect to Calcutta, okay. So this particular relative position is also important in this type of optimization problem. And this type of optimization problem, scheduling optimization problem, is different from the ordinary optimization problem like optimal design of gearbox or optimal design of the spring and so on. So the optimal design of gearbox, optimal design of spring, these are very simple optimization problem compared to your scheduling optimization problem, because here order and adjacency are also very important. The relative position of the cities are also important. Not only the distance, but also their relative positions are important. And that is why actually this ordinary GA or the binary coded GA which you have already studied, or simple genetic algorithm with the ordinary crossover operator like single point, 2-point, multi-point or uniform crossover are not going to serve the purpose. So you will have to use a special type of crossover operator, okay. So I am just going to discuss those special type of crossover operators which are to be used to solve this type of scheduling problem, okay. Now let me once again concentrate on the scheduling problem, that is TSP. Now the scheduling problem, it could be symmetrical. Now it is called symmetrical when Dij is equals to Dji, that is the distance between I and j is same as the distance between j and I. That means I have got two cities I and j. So from I to j there is a path or a route, and from j to I there is another route, but in both the routes actually the distance values are same. That is called the symmetrical TSP, okay. Now two types of TSP, one is called the fully connected TSP, another is called the partially connected asymmetrical TSP. Now if it is symmetrical TSP, it has to be fully connected, okay. Now, asymmetrical TSP will be partially connected. Now, here I am just going to show the schematic view for the fully connected TSP and asymmetrical TSP, that is a partially connected one. Now, here you can see between any two cities, say city 2 and city 6, I have got one path here 2 to 6, another path from 6 to 2. Okay. So, the two cities are connected in both the ways, any two cities are connected in both the ways, and that is called the fully connected TSP. Okay. And another condition, if Dij equals to Dji, that will become the symmetrical fully connected TSP. Okay. Now, this is partially connected asymmetrical TSP. You can see between cities 2 and 6, there is a path from 2 to 6, but from 6 to 2 there is no direct path, and that is called partially connected asymmetrical TSP. Okay. Now, this TSP involving n cities, there is a maximum of n factorial possible sequences. You can understand the complexity of this particular problem. Now, let me take a very simple example, you will understand the complexity of this particular problem. Supposing that I have got 3 cities, very simple example, 3 cities, city 1, 2 and 3. How many possible sequences are there? Now, let us see. Now, between 1, 2 and 3, now one connectivity could be 1, 2, one connectivity could be 1, 2 and 3, this is one connectivity. Okay. Another connectivity, another sequence could be 1, 3, 2. Then I can start with city 2, then 1, 3, then comes 2, 3, 1. Then I can start with city 3, I can go to city 1, then city 2, then I can start with 3, then 2, then 1. So, there are 6 possible sequences, you can see that 1, 2, 3, 4, 5, 6, and this 6 is nothing but is your 3 factorial. Now, supposing that I have got one TSP, travelling salesperson's problem, okay, having say 10 cities. 10 cities means how many possible sequences are there? 10 factorial, and 10 factorial is a huge number. So, there are so many such sequences, there are so many such possibilities, and out of all such sequences, so you will have to find out the best one, which is a difficult problem, because 10 factorial is a huge number and there are so many possibilities, and if you give this particular task to the GA, GA will take long time to decide what should be the optimized or the optimal sequence. Okay. So, this is a complex problem. So, this type of optimization problem is a complex problem. Okay. Scheduling problem is a complex problem, and as I told that we will have to use a special type of operator. Otherwise, what will happen if we use ordinary crossover operator like single point, 2 point, multi point crossover, there is a possibility you will be getting some infeasible sequences. Okay. You will be getting some solution. GA does not know the problem. Okay. The problem information you will have to inject to the GA. Okay. Now, GA will give you some solution which will have no practical meaning, and there could be a possibility you will be getting some infeasible solution. And if you want to ensure the feasible solution, so you will have to use some special type of operator, and those operators I am going to discuss. Okay. Now, here there is one comment, SGA with conventional crossover operators may not be suitable for the scheduling problems. So, I hope you have understood the real complexity of this type of problem, okay, and your ordinary crossover operator used in the binary coded GA or the simple genetic algorithm may not serve the purpose, and that is why we will have to use some special type of crossover operators. Now, here I am just going to discuss a few special type of crossover operators. The first one is your edge recombination. Now, this particular crossover operator edge recombination, that was proposed in the year 1991 by Whitley et al. They proposed this particular the crossover operator. Name of the crossover operator is edge recombination. please try to understand very carefully. Okay. Now, supposing that in crossover operator what happens? Some parents are going to participate in crossover and there will be some exchange of properties and there will be some children solutions created. Okay. Due to this exchange of properties, some children solutions will be created. Okay. And there will be diversification of the solution. Okay. Now, supposing that I have got two sequences as parent, like parent 1. So, there are 9 cities here, 9 cities mean 9 factorial, so many possibilities. Okay. So, parent 1, supposing that 1, 2, 3, 4, 5, 6, 7, 8, 9, parent 2 is 9, 3, 1, 4, 5, 8, 2, 6, 7. This is a very typical example, you can take some other example also. Okay. Now, supposing that, so this is parent 1 and parent 2. So, how to find out the feasible children solution using this age recombination operator, crossover operator. So, I am going to discuss that. Now, in this operator, so there will be one connectivity graph that is called the age table. So, this is the age table, city connectivity. So, you can see that city 1 is connected to so many such cities. Similarly, city 2 is connected to so many such cities, 3 is connected to 2, 4, 9 and 1, 4 is connected to 3, 5, 1, 5 is connected to 4, 6, 8, 6 is connected to 3 cities, 7 is connected to 3 cities, 8 is connected to 4 cities, 9 is connected to 4 cities. That means, this is not the fully connected network, this is the partially connected network and this shows the connectivity, okay, of the different cities. Okay. And here in the graphical form you can see the connectivity. Now, you will have to consider this particular age table or the connectivity table to decide what should be the children solution corresponding to the parents. Now, let me do one thing, let me write down this particular connectivity because I will have to show you how does it work. So, let me just draw this particular thing like city and its connectivity, city and connectivity. You can also prepare on the notebook city and connectivity. So, city 1 is connected to 2, 9, 3 and 4, 2 is connected to 1, 3, 8, 6, 1, 3, 8, 6, then 3 is connected to 2, 4, 9, 1, 3 is connected to 2, 4, 9, 1, 4 is connected to 3, 5, 1, 4 is connected to 3, 5, 1, then 5 is connected to 4, 6, 8, 5 is connected to 4, 6, 8, then 6 is connected to 5, 7, 2, 5, 7, 2, then 7 is connected to your 6, 8 and 9, 6, 8 and 9, then 8 is connected to 7, 9, 5, 2, 7, 9, 5, 2 and 9 is connected to 8, 1, 7, 3, 8, 1, 7, 3. Okay. Now, I will have to find out your the child 1 and child 2. Let me write down parent 1 and parent 2 here. So, let me write down the parent 1. Parent 1 is your 1, 2, 3, 4, 5, 6, 7, 8, 9 and parent 2 is your 9, 3, 1, 4, 5, 8, 2, 6, 7. Okay. So, these are actually the parent 1 and parent 2 and you will have to find out your child 1 and child 2. I am going to write here child 1 and child 2. Okay. Now, how to find out this particular child 1 and child 2 so that it becomes a feasible solution. Okay. Now, what we do here is we start with parent 1, the first city of parent 1. The first city of parent 1 is actually city 1 and I am trying to find out child 1. So, let me write here city 1 here. Okay. against child 1 I am going to write city 1. That means I have selected 1 as the starting city for child 1, and once I have selected child 1 or this city 1, so all the entries of 1 are to be removed from the right hand side of this connectivity table. Okay. Now 1 has been selected, so you remove 1 here, you remove 1 here, you remove 1, you remove 1 here. Okay. Now city 1 is connected to 2, 9, 3 and 4. Okay. City 1 is connected to 2, 9, 3 and 4. Now 2 is connected to 3 cities 3, 8, 6 because 1 has been deleted. Then 9 has been connected to 8, 7 and 3, 3 cities. 3 is connected to 3 cities 2, 4 and 9, and 4 is connected to 3 and 5, 2 cities. So out of these 2, 9, 3 and 4, city 4 is connected to less number of cities. Okay. So after 1 you select 4. Am I clear to all of you? See, once again let me repeat. City 1 I have selected. Now city 1 is connected to 2, 9, 3 and 4. We check the connectivity of city 2, 9, 3 and 4. Now 2 is connected to 3 cities, 9 is connected to 3 cities, 3 is connected to 3 cities, 4 is connected to 2 cities. So city 4 is connected to less number of cities. So after city 1 you select city 4. Okay, that means you select that city which is connected to less number of cities. Okay, and once you have selected 4, you remove all the entries of 4. So 4 is removed, 4 is removed, 4 is removed. So there is no other 4. Okay, now you see 4. You concentrate on city 4. Okay. Now 4 is connected to 3, 4 is connected to 5. Now 3 is connected to 2 cities, 5 is also connected to 2 cities. Okay. So there is a tie. Now for this tie you can select any one. That means after 4 you can select either 3 or 5, any one you can select. Okay. Now let me select 3. Now if I select 3, so you remove 3 from here, 3 from here, 3 from here, then 3 from here. Now you see the connectivity of city 3. 3 is connected to 2 and 3 is connected to 9. Okay. 3 is connected to 2 and 3 is connected to 9. Now you see 2 is connected to 2 cities, 9 is connected to 2 cities. Once again there is a tie. Okay. So after 3 you can select either 2 or 9. So let me select 2. You can also select 9. And once 2 has been selected, you remove the entry, 2 is removed, 2 is removed here, 2 is removed here, 2 is removed here. Now you see, concentrate on the connectivity of city 2. 2 is connected to 8 and 2 is connected to 6. Now 8 is connected to 3 and 6 is connected to 2 cities. So let us select 6 and remove all the entries of 6 here. 6 is removed, 6 is removed, 6 is removed. Okay. Now you see the connectivity of 6. 6 is connected to 5 and 7. Okay. Now 5 is connected to only one city, 7 is connected to 2 cities. Okay. So you select 5. Okay. So 5 is selected. So remove 5 from here, remove 5, remove 5. Then you see the 5. So city 5 is connected to 8. So 5 is connected to 8. Okay. You remove 8, 8, 8, 8. Now 8 is connected to 7 and 9. 7 is connected to 9, 9 is connected to 7. So anyone you can take, there is a tie. So let me take 7. If I take 7, so you remove this, 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 and 7 is connected to 9. So, this is one feasible child solution. You see all the cities have been considered only once. You check 1, 2, 3, 4, 5, 6, 7, 8, 9. All the cities have been considered once and there is no repetition. So, this is a feasible child solution and you can check also from the connectivity graph that this is a feasible solution. Okay. Similarly, what you can do to determine child 2, I can start with the starting city of parent 2. The starting city of parent 2 is 9. Okay. So, you can start with 9. You can start with 9. Okay. Now, once 9 has been selected, once again this connectivity table you will have to make and 9 has to be removed. Then you see city 9 is connected to which are the cities and you follow the same method. I think you have understood the method. Okay. So, by following that, so you can find out what is child 2. Okay. And once again you will be getting one feasible child solution. So, the problem of getting infeasible solution is not there if you follow this type of crossover operator, that is your edge recombination. Okay. So, I think I am clear to all of you, the method is clear to all of you. So, this is the way actually you can find out the feasible solutions from the parents. Okay. And if you do that, so there is no problem because order, adjacency, everything will be maintained and you can check from the connectivity graph that this is a feasible child solution. Okay. So, this is one operator, very popular operator for the serialing problem. Okay. So, here actually I have written whatever I discussed, I have written all such things, whatever I discussed here, the same thing I have written it here. Okay. So, I think you have understood, all of you have understood the method. Now, I am just going to discuss another operator that is called the order crossover. Okay. So, this is another operator that is called the order crossover. So, order crossover. Now, this was proposed by Davis in the year 1985. Now, here a part of one child solution is obtained by copying directly from a part of one parent and the other part of that child inherits the order of remaining elements of other parent. Okay. So, what you will have to do is you will have to select some crossover sites. Okay. Then to get the child solution, a few cities are copied from a particular parent and the remaining one will have to copy from the other parent. So, that there should be some exchange of properties. Okay. How to do? Let us see. Now, here I am just going to take one example. So, this is parent 1 and this is parent 2 and these two are the crossover sites and let us see how to find out the children solution, the safe children solution. Okay. So, let me write down parent 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, parent 2, 3, 4, 5, 1, 2, 9, 8, 7, 6. So, this is parent 1 and parent 2. So, you will have to find out child 1 and child 2. Okay. The crossover sites, those are selected at random using the random number generator. Supposing that the crossover site, the first crossover site is here and the second crossover site is here. Okay. Now, how to find out your child 1 and child 2? Okay. Now, let us see once again, let me read it out. A part of one child solution is obtained by copying directly from a part of one parent and the other part of that particular child inherits the order of the remaining elements of other parent. Okay. Now, here I have written the procedure: select two crossover sites at random, So, these two are the crossover sites which are selected at random. Now, if you choose some other crossover sites, you will be getting altogether different children solutions. Okay. Now, to obtain child 1, the elements 1, 2, 9, 8 lying between two crossover sites are directly copied from parent 2. So, this 1, 2, 9 and 8. So, these are directly copied from parent 2, keeping their location and order intact. Okay. So, what we do? So, I will have to find out child 1. So, I am directly copying. So, the cities which are lying between the two crossover sites, that is 1, 2, 9 and 8. Okay. 1, 2, 9 and 8 we are directly copying from parent 2. Okay. We can also copy from parent 1, there is no problem. For child 2 I will copy from parent 1. Okay. I can also do the just reverse also, there is no problem. Okay. Now, once you have copied this, now you see child 1 2 then begins from parent 1. So, this I have taken from parent 2 and I will have to take something from parent 1, then only there will be exchange of properties. So, child 1 2 then begins from parent 1, starting from the first position after the second crossover site. So, this is the second crossover site and first position after the second crossover site is this. Okay. So, the first position after the second crossover site, this is the second crossover site. So, the first position after the second crossover site and searching towards the initial elements of parent 1. Let us see what happens. So, I am just going to search from here. So, this is city 8, 8 has been already selected. You can see within the bracket I put 8, 1 to 9, 8. So, 8 is there. So, I cannot take it again. Next is city 9, 9 is also there. So, I cannot take it again. Next what you do, you come back to the starting city of parent 1, 1, city 1, 1 is also there. Then comes your 2, 2 is also there, we cannot take. Then comes your 3, 3 is not there. So, this particular vacant position you put 3 here. Okay. The next is 4, 4 is also not there. So, you put 4 here. Okay. Next is 5. So, 5 is also not there. So, you put 5 here in this particular position. Next is your 6. So, you put 6 here. Next is your 7. You put 7 here. Okay. And now we can check all the cities have been considered like 1, 2, 3, 4, 5, 6, 7, 8, 9 and there is no repetition of the cities. You can check that there is no repetition of the cities. Okay. Now, similarly to get the child 2, what we do is we first copy from parent 1. So, we copy from parent 1, that is your 4, 5, 6, 7 we copy from parent 1 and now I will have to copy from parent 2. Okay. And once again I will start with the first city after the second crossover site, that is your 7. So, this is the starting position of the search. Am I clear? So, this is the starting position of the search, first city after the second crossover site lying on parent 2. Okay. So, the first one is 7, 7 has been selected. Then comes your 6, 6 is also selected here. Then we go back to the starting 3, 3 is not there. So, you put 3 here. Next is 4, 4 is there, 5 is also there. Next is 1, so you put 1 here. Next is 2, 2 is not there, so you put 2 here. Next is 9, 9 is not there, so you put 9 here. Okay. Next is 8, 8 is also not there, so you put 8 here. Okay. Now, you can check 1, 2, 3, 4, 5, 6, 7, 8, 9. So, all the cities have come and there is no repetition. Am I clear to all of you? Huh? So, the method of this particular order crossover, I think this is clear to all of you. Okay? Please.
Sir, in this method, does the in here we can get infeasible solutions.
Pardon?
In here we can get infeasible solutions.
You can try whether you can get infeasible solution or not. You will not be getting infeasible solution. No, you won't be getting infeasible solution. Huh? Yes, we are checking. No, one after another we are checking. And I will give you one task. Whenever you find time, you just check. You just change that particular the crossover locations, crossover sites. Okay, the same problem you take parent 1 and parent 2. Take the crossover site, the first crossover site you take here and the second crossover site you take here. Now only you can try. You take the first crossover site here, this is the first crossover site and this is the second crossover site, you can take it here. Okay, and you can try to find out what should be your child 1 and child 2. Please spend some time. Otherwise, things will be confused, you will be confused. Okay. Take the two crossover sites, one is like this, another is like this. All of you, please try. Write down parent 1, parent 2.
In this method, the whole generation will have the middle 4 edges constant.
Now, it depends on the crossover sites are selected at random using the random number generator. Okay, sometimes the way I selected the crossover site first, that will be the crossover site. Next time the crossover sites could be different, because crossover sites are selected at random using the random number generator.
Otherwise, it is not desirable to have the same generation, no?
Same?
Generation, like same constant this in the generation.
You see, you just check with the second set of crossover sites, solution will be different. So, you will be getting different solutions. Got it? Good. So, you people are getting, I think. So, similarly, if you take some other crossover sites, other combination of the crossover sites, you will be getting the different the children solutions. Okay, and you will be getting the feasible solutions. Okay. So, I think this order crossover is clear to all of you. Okay. Is there any doubt of this order crossover? Yes. I am coming to that. I will be discussing at the end. After discussing all the crossover operators, okay, I will be coming to that particular comment. Which one is better? Which one is better? In fact, we studied a lot on this. In fact, there is one BTech project on this. So, all the operators we tested. We also proposed one operator, and that is also tested on a number of problems, and we came to some conclusion. I will be coming to that, okay, at the end. Now, next is the cycle crossover. So, cycle crossover. Now, it was proposed by Oliver et al. In the year 1987. Here, the absolute position of elements of a parent are preserved while determining a child solution. Okay, and let us see how does it work. How does it work? Let us see. Now, let me consider the parent 1. Parent 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9. Then comes parent 2, that is 3, 4, 5, 1, 2, 9, 8, 7, 6. Okay. And let us see how to get the children solution using the cycle crossover. Now, remember the cycle crossover, this will start from a particular city, okay, and here the starting city or the starting of the cycle is denoted by a star. So, here I have put star. So, this is the starting of the cycle. Okay. This selection is random. You can take any one as the starting of the cycle. This selection is at random. Okay. Now, let us see how to get this particular thing, but before that let me read this procedure, then I will explain it here. Okay. To determine child 1, we are going to determine child 1, select a parent, say peer 1, and the starting position of the cycle, that is the third at random. So, this is the starting position of the cycle. So, this is the starting position of the cycle, and I am trying to find out what is your child 1 and child 2. Child 1 and child 2 I am trying to find out, and the starting of the cycle is your CT3. Okay. Thus, the child 1 position 3 is equals to 3. Child 1 position 3 is equals to CT3. So, let me just write down here child 1 and the child 1 position 3 is equals to 3. So, this is your CT3. Okay. So, I have got how many positions? 9 positions, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, the third position I am writing CT3. Okay. Then peer 2 is then searched to check. Now, this is taken from parent 1. Okay. This is taken from parent 1. Now, parent 2 is then searched to check the presence of element 3, and it has been found in the first position. So, 3 has been selected. Now, you check the occurrence of 3 on parent 2. So, this is the occurrence of CT3 on parent 2. Okay. And book this particular position, that is position 1. Okay. And in this particular position you put CT1. Okay. So, you put CT1. That is why the child 1 position 1 is nothing but parent 1 position 1, and that is equals to 1. Am I clear to all of you? Shall I repeat it once again? Let me repeat. I have got parent 1 and parent 2, and there will be a starting position for this particular cycle. Supposing that the starting position is 3. So, this is the starting position. Okay. Now, to get child 1, we take the help of parent 1 first. Okay. So, these 3 you directly copy, and once you have copied these 3 here at location 3, now you find out the location of CT3 on parent 2. So, this is the location of CT3 on parent 2, that is location 1, and the CT corresponding to parent 1 at location 1 is CT1. So, I am putting CT1 here. Am I clear? Now, you find out the yes.
Sir, what if I choose 4? Then I have to put 4 on the 4th position.
2 will come here.
No, sir. Say
If I take 4, so 4 will come here, 4 will come here. Are you getting my point? Then you will have to find out the possible location of 4. So, 1 has been selected, 1 has been selected. Now, you find out the possible location of CT1 on parent 2. So, this is the location of CT1 on parent 2, and its corresponding CT on parent 1 is 4. So, you put 4 here. Okay. And once 4 has been selected, you find out the location of 4 on parent 2. So, this is the location of 4 on parent 2. Okay. And its corresponding CT on parent 1 is 2. So, you put 2 here. Then you search for 2. So, this is the location of 2 on parent 2, and its corresponding CT on parent 1 is 5. So, you put 5 here, and once 5 has been selected, now you find out the location of 5 on parent 2. So, this is the location of 5 on parent 2, and its corresponding CT is 3. 3 has been selected. So, it completes the cycle. The cycle is completed now, and you see on child 1 all such CTs like 1, 2, 3, 4, 5 we have taken from parent 1 only. You can check that 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 all are taken from parent 1. Okay. So, the remaining positions or the vacant positions are to be taken from parent 2. So, you take from parent 2. Okay. So, if you take from parent 2, so this will become 9, 8, 7, 6. Now, you check 1, 2, 3, 4, 5, 6, 7, 8, 9. So, all the cities we have selected and there is no repetition, isn't it? So, this is one feasible child solution. Am I clear to all of you? Similarly, I can also find out what is child 2. What is child 2 I can find out. So, let us try to find out child 2. So, for child 2, the starting city I will have to take from parent 2 and that is your 5. Okay. So, let me put 5 here, there is no problem. Okay. That is the starting of the cycle. Now, you find out the possible location of city 5 on parent 1. So, this is the possible location of city 5 on parent 1. Okay. So, you book this particular position and take the city corresponding to parent 2, that is your 2. So, you put 2 here and once you have selected 2, you find out the location of city 2 on parent 1. So, this is the location of city 2 on parent 1 and its corresponding city is 4. Okay. So, you put 4 here. Then you find out the location of city 4 on parent 1 and its corresponding city is 1. So, here you put 1. You find out the location of city 1 on parent 1. So, this is the location, its corresponding city is 3. So, you put 3 here. Then you find out the location of city 3 on parent 1. So, this is this, okay, and its corresponding city is city 5, 5 has been selected. So, it completes the cycle. Okay. And here this 3, 4, 5, 1, 2, 3, 4, 5, 1, 2 are taken from parent 2. So, rest of the things I will have to taken from parent 1. So, you put here 6, 7, 8, 9. Okay. And now, you can check 1, 2, 3, 4, 5, 6, 7, 8, 9. So, all the cities have been taken, all the cities have come and there is no repetition. Is it clear to all of you? Okay. Now, if it is clear, now once again please write down parent 1 and parent 2, same parent 1, parent 2 you write down on your notebook, you write down parent 1 and parent 2. Parent 1 and parent 2 you write down. Please.
Parent 2 was 4, 5, 3 instead of 3, 4, 5. What would have happened? Parent 2.
4.
4, 5, 3, 1, 2.
Then what will happen? Then starting, then cycle will stop. Cycle will stop and you will be getting all the things, only the first element you can take as 3, okay, and other things you will have to take from the other parents. So, the diversification of the solution will be lost. You see, yes. Now, that will be there, but new information is not going to come. See, for efficient use of GA, there should be population diversity and the selection pressure. There should be a proper combination. Okay. I think you have studied that. There should be a proper combination of population diversity and selection pressure. Unless there is a proper combination, the GA search is not proper. Now, if that is the situation, then diversity will be lost. New solutions are not coming. Might be selection pressure could be too high and there could be a chance of premature conversion. You want to reach that highest position as early as possible without doing anything. The highest position if you reach in 2 years, might be you do not know anything, but you have reached the highest position. You will not be able to perform properly. So, that is called the premature convergence. So, there will be a chance of premature convergence if you get that type of situation. because for efficient use of the GA, there should be a proper combination of population diversity and selection pressure. Okay. Now, I think you have written parent 1 and parent 2. Achha. Now, you take fifth as the starting. In place of third, you take fifth as the starting. You put one star. On fifth position, you put one star. Okay, and try to implement the cycle crossover. Please spend some time. Take fifth as the starting position of the cycle. Are you getting the same answer? Same child you are getting? Achha. This is a very hypothetical situation that you are getting the same. All of you are getting the same answer? Anyway, you got the idea, no? So, how to get this particular children solution from the parent, that is more important. Okay. The next operator is known as the position based crossover, and that was proposed in the year 1991 by Sisbarda. Now, here I am just going to consider this is parent 1 and this is your parent 2. Okay. Now, let us see the procedure to determine child 1. To determine child 1, choose a number of crossover points, say 1st, 4th, 7th and 9th on parent 1. Okay. So, we are choosing a number of crossover points. For example, the first one, then comes your 4th, then comes your 7th, then comes 9th as the crossover points. Okay. And those are selected at random. You can select any other 4, any other 3, any other 5. Okay. Supposing that these are selected at random, okay, using the random number generator. So, these are selected. Now, to get child 1, so how to get child 1? To get child 1, so I have got 9 position 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, the elements 1, 4, 7 and 9 are directly copied from parent 1. Okay. 1, 4, 1, 4th, the first, 4th, 7th and 9th elements. So, those are directly copied from parent 1. Okay. So, I am putting 1 here, I am putting 4 here, I am putting your 7 here, I am putting 9 here. So, this 1, 4, 7 and 9 are directly copied from parent 1. Okay. Now, next is the remaining elements of child 1 are selected from parent 2. Okay. So, 1, 4, 7 and 9 have been selected from parent 1, and the rest of the things we select from parent 2. Okay. So, we will start from here, from parent 2, the starting position of parent 2 will start from here. Okay. The first is CT3, 3 is not there. So, you select 3 here, first position I have already selected 1. So, you select 3 here. The second is 4, 4th is there. then city 5, 5 is not there, select 5 here. Then comes the first city is already there, second city is not there, so you select there, city 9 is there, city 8 is not there, so you put it here, city 7 is there, then comes 6, so 6 is here. Okay. Now, then comes your child 2. Child 2, how to get child 2? So, here, so this 3, 1, 8 and 6 you will have to select from parent 2. Okay. So, let us select 3, then comes your 1, then comes your 8 and 6. So, those are selected. So, 3, 1, 8 and 6 are selected from parent 2. Okay. So, these are the remaining sites. So, you will have to select some city for this particular the remaining sites. How to select? What you do is you start your search from parent 1. So, you start from here. Okay. So, the first is 1 has been selected. Next is your 2 is not selected. So, you can take 2 here. Next is 3 is already selected. Next is 4, you can select 4 here. Then comes here 5, I can select 5 here. Then comes 6 is already there. Then comes your 7, so this is position 7. Then comes 8 is already there. Then comes your 9, so 9 you can put here. And you can check 1, 2, 3, 4, 5, 6, 7, 8, 9. So, all the cities have been selected, okay, and there is no repetition. Okay. I think this is clear to all of you. Okay. Now, what you can do, once again on the notebook you can write down parent 1 and parent 2, write down parent 1 and parent 2. Write down parent 1 and parent 2, write down parent 1, 1, 2, 3, 4 up to 9, parent 2, 3, 4, 5, 1, 2, 9, 8, 7, 6, parent 2 you write down 3, 4, 5, 1, 2, 9, 8, 7, 6. Okay. Now, you select the position like second position, fifth position and 8th position. You put star second, fifth and 8th. Second, fifth and 8th you put the star and try to find out the children's solutions. Got it? No? Okay. You will be getting, you follow the same method. Answers are different. Okay. Now, I am going to discuss another method, another crossover, that is called partially mapped crossover, in short that is called PMX, and that was proposed in the year 1985 by Goldberg and Lingley. Now, here the method is slightly difficult to understand. So, listen to me very carefully. Okay. A part of a parent solution lying between two crossover sites is directly copied into a child solution. That part is simple. Okay. Now, let me write down parent 1 and parent 2. Parent 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9. Then parent 2 is your 3, 4, 5, 1, 2, 9, 8, 7, 6. And the two crossover sites are selected at random. One crossover site is here and another crossover site is here. Okay. Now, select two crossover sites at random. The elements 4, 5, 6 and 7 of parent 1 lying within two crossover sites are directly copied to child 1. That means your, so if you want to find out child 1, so these things are directly copied, that is your 4, 5, 6 and 7, these are directly copied. Okay. The next is your, to determine the remaining elements of child 1, the search starts with the elements of pair 1 residing in between the two crossover sites. Once again, to determine the remaining elements of child 1, the search starts with the elements of pair 1 residing in between two crossover sites. So, I will have to start the search from here. Am I clear? Now, the element pair 1 4, pair 1 4 is 4 is located at second position of pair 2, second position of pair 2, yes, second position. Thus, the second position of child 1 will be filled up by an element of pair 2 located at fourth position, that is CT 1. So, this is as follows, you see. So, this is parent 1 and parent 2, select the crossover sites which are selected at random, crossover site 1, crossover site 2. To get child 1, you directly copy the cities which are lying between the two crossover sites like 4, 5, 6 and 7. You copy 4, 5, 6 and 7. Then the search will start from the first city lying between the two crossover site on parent 1. That means, it will start from here. So, that is 4, city 4. You find out the location of city 4 on parent 2. So, this is the location of city 4 on parent 2. Okay. So, at this particular position, that is the second position, you write down city 1, because 1 corresponds to 4. Okay. So, you put city 1 here. Let me repeat it again. So, here there is a 4, find out the possible location of 4 on parent 2. So, this is the location, second location. So, second location you put the city 1, because 1 corresponds to 4 here, lying between the two crossover sites, city 1 corresponds to city 4. So, you put 1 here. Next you go to 5. So, this is the possible location of 5 on parent 2, and at this location you put city 2, because 2 corresponds to 5 here, put 2 here. Okay. Next is your city 6. You find out the possible location of city 6 on parent 2. So, this is the possible location. At this location you put city 9, because 9 corresponds to 6. So, you put 9 here. Then 7, this is the possible location of 7 on parent 2. So, you book the location and you put the city, 8 corresponds to city 7. So, you put 8 here. Okay. And what is the remaining city? The remaining vacant position is only 1. There is only 1 vacant position, and this you take from parent 2. Okay. Parent 2, there is a 3 here. So, you put 3 here. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, you are getting a feasible solution. But here in this method, there is absolutely no guarantee that every time you will be getting feasible solution. There is a chance you will be getting infeasible solution, and if there is infeasible solution, you will have to make some correction. How to do that? I am going to tell you. Now, similarly, how to get child 2? Child 2. Let us try to find out child 2. Now, to get child 2, first you copy this 1298. 1298 you copy. Okay. Now, you start your search from 1. This is the location of 1 on parent 1. So, you just book that location and put city 4 there, because 4 corresponds to 1, 4 here. Next is 2. So, this is the location of 2, book the location and you put 5 here. So, 5. Next is 9. So, this is the location 9. So, this is the location 9 and here you put 6, put 6 here. Next is 8. This is the location of 8 and 8 corresponds to 7 here. So, you put 7 here. Okay. And the rest of the thing you copy from parent 1. So, this is the only vacant position. Okay. So, there you put 3. Now, you see 1, 2, 3, 4, 5, 6, 7, 8, 9. So, feasible solutions we are getting, but as I told that every time you may not get the feasible solution. For example, say here there is, I have put one example, you can see here you will not be getting the feasible solutions. Okay. For example, say parent 1 and parent 2, 1, 2, 3, 4, 5, 6, 7, 8, 9 and parent 2, 3, 4, 5, 1, 2, 9, 8, 7, 6. The crossover sites are here and here. Okay. Now, if you use this PMX, there is a possibility you will be getting the child solution as follows. So, child 1, first you copy directly from here. So, this is 3, 4, 5, 6. Here there are 2 locations, here there are 3 locations. So, 3, 4, 5, 6. Now, you start your search from here. 3, this is the possible location of 3, 3 corresponds to 5. So, you put 5 here. Then comes 4, this is the location of 4, 4 corresponds to 1, you put 1 here. Then comes 5, but 5 is, this is the location of 5, but it is lying inside that particular the crossover site which has been selected. So, you can't do anything, do not do anything. Next is 6, 6, this is the location of 6 and this is your 6 corresponds to 9. So, you put 9 here. Rest of the things you take from parent 2, that is 8, 7. Okay. Similarly, child 2. So, directly you copy this 5, 1, 2, 9, 5, 1, 2, 9. Then you start your search from here. First is 5. 5 is already there within the crossover site. So, you can't do anything. Next is 1. So, this is the location of 1 and 1 corresponds to 4. So, you put 4 here. Next is 2. This is the location of 2. 2 corresponds to 5. So, you put 5 here. I am coming to that. Next is 9. This is the location of 9. So, 9 corresponds to 6. You put 6 here. Okay. And the rest of the things you will have to take from your parent 1, 7, 8, 7, 8. And now you can check, you are getting some infeasible solution here. You see child 1, 1, 2 is missing, 3, 4, 5, there are 2 5s, 6, 7, 8, 9. There are 2 5s and out of 2 5s, one is lying inside the bracket, another is outside bracket. Inside bracket, do not change it. Outside bracket, you change 5 to 2. 2 is missing. Okay. So, 5 1 will become 2 1. Okay. Similarly, child 2, 1 2, 3 is missing. there are two pipes, inside bracket don't change, outside bracket you change it to 3. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So, if you use this type of crossover operator, so you will have to make some modification. Okay. We also proposed one crossover operator, which is very simple, the modified version of single point crossover, that is very simple. Now, I am coming to your point, which one is the best? As I told that we tested on a number of problems, all the methods including our proposal, okay. But we saw that the performance of this particular crossover operator is found to be problem dependent. So, you cannot give guarantee that this method is the best. We could not give any such guarantee that whether cycle crossover is the best or order crossover is the best. It was found to be problem dependent. Okay. So, we could not come to that type of conclusion that this particular method is the best. Okay. So, this is the way actually we will have to design the crossover operators. If you use genetic algorithm to solve the scheduling problem, and scheduling problem as I told is much more difficult compared to your ordinary optimization problem like spring design, gearbox design, that type of thing. In fact, I call it this is a vector optimization problem, where spring design, gearbox design, these are all scalar optimization problem. Okay. So, please.
Can we use this operator in binary coded chromosome?
We can, but there will be a lot of processing, you will have to convert it to real and that type of thing. Better to use, you see CT number like 1, 2, 3, 4 is better to write 1, 2, 3, 4 like this, and you can do accordingly. You can also do binary, binary is also possible, but that conversion you will have to do. Binary to your see corresponding to CT9 you will have to write one binary, 8 you will have to write one binary, you will have to convert it to this, whenever required you will have to convert it to 8, 9, some that problem will be there. Okay. Better to avoid that. I think this is clear to all of you, the different, and one thing you just try to understand that if you are going to solve the scheduling problem, okay, another example could be a class routine. Class routine, it is a very difficult optimization problem, okay, which is almost similar to the scheduling problem. Okay, it is not so easy like gearbox design, optimal design of gearbox. Okay, it is better to use this type of operator. Then the chance of getting the feasible solution is more. Otherwise, if you use the ordinary binary, your single point, 2 point, multi point crossover, so you will be getting lot of infeasible solutions, and you will have to penalize those infeasible solutions by the penalty terms. Okay. And you know how to tackle the penalty in genetic algorithm. Okay. So, you will have to use that particular thing. Yes. Yes. See, what is this solution? Solution means the different sequences. As I told, there are 10 cities. So, there are 10 factorial solutions, a huge sequence, huge number of possible sequences. Now, using GA, we are trying to find out which one is the best, which one is the optimal. So, optimal solution will be a particular sequence. A particular sequence of the cities will be the optimal solution, or there could be multiple solution also. See, this is what I discussed is the crossover operator. Inside GA, we have got reproduction crossover. You can skip mutation operator for this type of problem, because if you use mutation, there is a problem, like sometimes you will be getting some infeasible solution. Mutation will give some infeasible solution. So, if you want to solve the scheduling problem, so you will have to go for reproduction and crossover, that is all.
So one thing, in this kind of problems, like we get the parents from where we bring out this children, right? So each of the children will then calculate the time.
We will have to find out the fitness value. So, corresponding to one child solution, what should be the total distance travelled, that you will have to find out. Corresponding to another, see I have got a population of solution. Using crossover operator, I am getting the population of solution size, supposing that size is 100. So, for each of these particular children solutions, I am getting that fitness information, which is nothing but the distance.
So this fitness information that will converge, or it can be like suppose it converges, like at least a minimum, or then again it starts increasing.
See, in the population there will be so many such solutions, it will have some fitness information. Supposing that I am running GA per 100 generation, might be at 50th generation I have got some optimal solution. After that it may improve, may not improve. If it improves, good. If it does not improve, that will be the optimal solution.
So then when will we know when we have to stop this iteration?
Generally, we use some stopping criteria as the maximum number of generation or the desired accuracy in the solution. Most of the time we use some fixed number of generation, like 100 generation, 200 generation, and then let the GA run for 200 generation. Whatever solutions we get, we declare that is the optimal solution. Yes.
Sir, how to put the constraint, like we have put in the first one, the edge recombination method, that one can only go to 2, 3 or 4.
Huh.
In rest form method,
If you, by using this, if you find some infeasible solution, for example, if you use PMX, there is a chance you will be getting some infeasible solution also. If you get infeasible solution, you will have to check it, make it feasible. Either you use order crossover, cycle crossover, or position based crossover, or PMX, or edge recombination. Always you will be getting feasible solutions. So, you need not use the penalty function approach or some other approach. But if you use ordinary crossover operator like multi-point, 2-point, there is a chance you will be getting infeasible solution, and infeasible solutions you will have to penalize. Might be you will be getting some solution 5 to 6, but supposing that this is a partially connected network, 5 to 6 there is no path. So, that type of solutions you will be getting, that solutions you will have to penalize.
that thing is already taken account in all these codes, sir. In first one we have actually manually done all those things.
Manually is done, but due to the crossover you will have to be careful that whether you are getting the feasible solution or not. To get the feasible solution, this type of special type of crossover operator you will have to use. That is why I discuss all such special type of crossover operator. Okay, please.
Sir, in case of bigger problems, suppose we have put a constant on L-dimensional vectors. Now, when we are interested to find the fitness value in 2-dimensional, 3-dimensional, then we use the fitness value obtained from that, from L-dimensional values, or do we modify our constant violations?
Now you see, in higher dimension there is a fitness, because GA is working on the higher dimension. It corresponding lower dimensional points I have got. Are you getting my point? I can also find out its fitness in lower dimension. Now this has to be mapped back using the reverse mapping, means once again I am going back to the higher dimension. Once again GA will work only on the higher dimension. Are you getting my point? GA is calculating the fitness only in the higher dimension. It is not calculating fitness in lower dimension. Okay? Please. Hmm.
But we are not checking the sequence, because maybe there is no route in between 2 or 1 or
Now, if you use this type of crossover operator like order crossover, cycle, PMX and all such things, PMX there is a possibility sometimes you will be getting infeasible, but if you use edge recombination, order, cycle and that type of thing, you will be getting the feasible solutions.
in feasible solution we are just checking they are coming 2 times or 3 times.
If they come 2 times, then it is infeasible, we will have to make some correction. The way I did for the PMX, we will have to relook into that, because that is the infeasible solution, because one city is coming twice and there is some missing city. So,
It doesn't go from 6 to 7 and you get a child solution from 6 to 7.
no, my point is if you use edge recombination, the connectivity graph, that type of solution will not come at all, you need not worry at all. That is why we are using this special type of crossover operator.
So perhaps we get such solution for PMX. Then
PMX, if you get infeasible, you will have to make some correction. You will have to check it, what type of child you are getting. So, inside the code, you will have to write those logic. So, once you have got child 1 and child 2, you will have to check whether a city is coming more than once, whether there is any missing city. For that, you will have to write down the algorithm. If if there is a missing city, or if a particular city is coming more than once, you will have to make the correction. You will have to correct child 1 and child 2, then proceed.
Sir, suppose that in the PMX only, we get a certain sequence where there is one point where 5 and 6 are not connected, but 5 and 6 are there, but there are no repeating sequences.
Then you will not be able to find out the fitness. You will not be able to calculate the fitness, because 5 to 6 there is no path, you do not know the distance, this thing will stop there. So, this is infeasible solution. Okay. That is the indication. You can penalize also that if you want. If it is a minimization problem, put a very high value, high positive value. If it is a maximization problem, you put some high negative value. Okay. It is a very simple penalty function approach. I think you have been taught now that static penalty, dynamic penalty, adaptive penalty. Generally, we use 3 types of penalty functions. Okay. Please.
Sir, in order crossover, cycle crossover, and position based crossover, in case of a partially connected asymmetrical pair,
there could be a problem.
So these methods may not be feasible solutions.
Generally, you see, for partially connected is better to go for edge recombination, but for the fully connected network, we can go for order and others. For partially connected network, if you get infeasible solution, you will have to penalize.
Then these methods are not suitable.
Now, generally we get, most of the time we get your fully connected network. See, Calcutta to Delhi there is a route, Delhi to Calcutta there is another route. Generally cities are connected in both the ways. Okay. Yeah. See, GA is a huge search. As I told, no, the 10 factorial, so many sequences, GA is going to search. Okay. So, out of all 10 factorial sequences, it will try to find out the best one. That is why I told, no, sometimes it takes few minutes, sometimes few hours, sometimes few days.
So for one person we get one result. Suppose we use for next iteration, for next problem, we use another crossover. So that final answer might get different.
You see, as I told, that sometimes you will be getting the same fitness multiple solution, that is also possible. GA can give multiple solution also. We will see the fitness. Whether we are getting the same fitness or different fitness, we will see that. Okay. If sometimes you will be getting multiple solutions having the same fitness values in GA. That is another advantage of GA. If you get multiple solution having the same fitness, that means you are getting multiple optimal solutions, any one you can choose. Okay. So, I think I am clear to all of you. Second half we are going to start at 2. There will be a test based on whatever I discussed today. So, there will be a test. So, please come prepared at 2. Okay. Might be 45 minutes or 1 hour maximum. So, there will be a test. Please come.